Alright, so today we're going to be looking at geometric sequences. Now, you should already be somewhat familiar with arithmetic sequences, so you know we're looking at patterns, right? We've talked about patterns being the building block of all of mathematics. So that's what we're looking at again today, is some patterns, but this one's going to be slightly different from the arithmetic one that we saw before. We're still going to have a sequence of numbers, and we're still going to be trying to predict what the numbers will be after a very large range. And so again, we're looking to see if we can find some way to create an equation for the general term. All right, so let's start with this one, which will be a little bit simpler one. It starts with 2, 10, 50, 250. So I'm going to ask the same question that I asked before in the previous video. If I wanted to try to predict the next number or the next numbers, what information would be important? Well, of course, you need to know what the pattern is. We're looking for some type of pattern. Okay. Now, even with a pattern, that's not quite enough because you need to know what you're starting from. Right? So if I know the starting number and I know the pattern, if I want a specific term, I also need to know how many terms there are, which term I want. Okay, so we're going to add on the number of terms. Okay, so now at this point, I could say I want the 100th term of this specific pattern, and you should be able to figure it out. Well, let's find out the pattern. Well, if you look at this one, we can tell already that it's not a constant difference, right? 10 minus 2 is 8, 50 minus 10 is 40. That's already not constant. But most of you have probably already recognized that there is still a pattern, and that the pattern is that each time I'm going to multiply by 5. 2 times 5 is 10, 10 times 5 is 50, 50 times 5 is 250. So we are multiplying by 5 each time. Oops. Very good. So let's do what we did before, and let's write down the first few terms and how we got them. Okay, so the first one, which we defined before as being U1, was just 2. Right? So again, that's something that we have, U1. Okay, the second term, U2, was just 2 times 5. Right? It was U1 times 5. Okay, the third term, now, I recognized that it was 10 times 5, but where did that 10 come from? Well, the 10 came from 2 times 5. So it's 2 times 5, which gives me the 10, times 5 again. All right, and then U4, of course, is U3, which is all of that. So 2 times 5, which is 25 times 2, which is 50, and then times 5 one last time. Okay? So if we look at this, we recognize that there is a pattern, right? And so we're going to try to create an equation for the general term, so UN. Now we look at this, we see obviously the first number is there every time. That's our U1. So write down U1. Now it looks like I need to multiply by 5 every time. So 5 is our pattern. Now in this case, it's not a constant difference. What it is a constant multiplier. We're going to call it a constant ratio. Now the reason is, remember before when we were doing arithmetic, we did the second number minus the first one. Remember, D was defined as UN plus 1 minus UN. So we took each number and we subtracted the number that was before it. Okay, so same thing here. Even though it's multiplying by 5 each time, by definition, the constant ratio is going to be the second number divided by the first one. So R is UN plus 1 over UN. So any number divided by the one before it. If that's always the same, 50 divided by 10 is 5, 250 divided by 50 is 5. If that number is always the same, then it's a constant ratio and the sequence is geometric. All right, so in this case we've got U1, which is going to be multiplied by R. But you'll notice that that doesn't quite work, right? Because if that were the case, then U1 would be U1 times R. U2 would be u1 times r. So we've got to kind of get this in there somewhere, and so the natural choice would be, okay, well, here's 1 5, there's 2 5s, there's 3 5s, right? So this was r to the first, this was r to the second, this was r to the third, right? And so from there, we say, okay, how is this related? What's changing here? Well, it's the n that's changing, right? You'll notice the n here is 2, and there's 1. 3, 2, 4, 3. So each time, this number right here is just 1 less than n minus 1. So we're going to rewrite this as being r to the n minus 1, which of course means for u1, that would be r to the 1 minus 1, which is r to the 0, which leaves us with just u1. Here it would be 2 minus 1, which would be u1, which is 2, times r to the first, and r is 5, so that would be 2 times 5, which is 10. So this is the pattern that will work. This is the equation for the general term for any geometric sequence. All right, remembering that r has to be a constant ratio. Okay, so we're going to go ahead and skip up here, and we'll do it again. Okay, so we're going to go through a little bit faster this time. So this time, what is the pattern of the sequence above? Okay, hopefully you're recognizing that every time we are dividing by 2, as we go from 8 to 4, we divide by 2, divide by 2, divide by 2. Now, some of you are already thinking in terms of r. Okay, now how in the heck does division and multiplication both give us the same thing? Well, remember that division is just multiplying by the reciprocal. So instead of divide by 2, we could also say that we are multiplying by 1/2, right? Multiplying by the reciprocal. So again, let's just write down the first terms. So u1 equals 8, u2 equals 8 times 1/2, or divided by 2, u3 equals 8 times 1/2, right? Because it's u2 times 1/2 again. u4, of course, was 8 times 1/2 times 1/2, right? 8 times 1/2 is 4, times 1/2 is 2, and then times 1/2 again to get to the fourth step. All right, now you'll recognize here almost exactly the same pattern that we had before, and that is because, of course, we're going to be multiplying by the same ratio every time. Note that 4 divided by 8 is 2, which is why r is, 4 divided by 8 is 1/2, which is why r is 1/2. Remember, r, as we defined before, was un plus 1 divided by un. So any number divided by the number before it. And so because of this, we know that 4 over 8, 2 over 4, and 1 over 2 are all the same. And so that then is a conjecture that shows that this is a correct pattern. It's a correct general statement. Okay, we haven't proven it for every single situation, but it has worked in the ones that we've used so far. Our conjecture or our thought is that because of this, it should work in all situations. All right, so let's go ahead then and write out our general. So un, again, equals u1 times r to the n minus 1. Okay, remember again, you have to have that n minus 1 because for u1, you've already got u1 there, but you're not multiplying by r to the first. You want to make sure to leave that out. All right, so that should work out. So can we determine a general equation? Yes, we just did. So again, in this case, un equals 8 times 1/2 to the n minus 1 power. And that will help us get anything. Now from here, you can plug in the number, you can plug in a value, you can plug in whatever you want, and you should be able to get different pieces out. All right, so I'm going to just leave it at that. Just remember that we have two different things that we're looking at. One is our general statement here for geometric sequences. And then the other one is this, which is for the constant ratio, which will also be very helpful as we're going through our problems. Okay, so that's it. I hope that's helpful. Get to work.